In this video, we're going to discuss measures of position, which will help us find outliers in our data set. I'm assuming that you've already watched the videos on measuring the center, measuring the spread, and the empirical rule. So now we're going to talk about z-scores, which go along with the mean and standard deviation. For the median and quartiles, we also have the LOB and UOB, which stands for the lower outlier bound and the upper outlier bound. But what is an outlier? It's a value that lies outside the rest of the data, either much smaller or much larger. So if we're looking at a data set, how do we know if something is an outlier? That's where the z-scores and outlier bounds come in. The z-score tells how many standard deviations a particular individual data value is from the mean of the data set. You can see the formulas there, and we have a formula for both the sample and the population. The x in the formula is the individual value that we're interested in. If it's too far away from the mean, then it's an outlier. But how far away is too far? If the data is bell-shaped, based on the empirical rule, any point that is more than 2 standard deviations away from the mean is unusual. Therefore, if z is less than -2 or greater than 2, then the point is an outlier. Here's an example, going back to the IQ example. IQ scores are normally distributed with a mean of 100 and a standard deviation of 15. My brother's IQ score is 142. That's a true story. Is this unusual? 142 is the score I'm interested in. That's our x. We plug that into the formula, so I have 142 minus the mean of 100, and then I divide that by the standard deviation of 15 to get a z-score of 2.8. That tells me my brother's IQ score is 2.8 standard deviations above the mean. Anything more than 2 standard deviations away from the mean is unusual, so an IQ of 142 is unusual. Next, we'll talk about outlier bounds calculated from the quartiles. This is the formula for the IQR, which stands for the interquartile range. It's the difference between the third quartile and the first quartile. We'll use this value in our formulas for the outlier bounds. Here are the formulas for the LOB, lower outlier bound, and the UOB, upper outlier bound. We take 1.5 times the IQR and subtract it from the first quartile to get the LOB, and we take 1.5 times the IQR and add it to the third quartile to get the UOB. Any data value that is less than the LOB or greater than the UOB is an outlier. Let's look at an example. Here I've listed 26 numbers, and I've already put them in order from smallest to largest. And they're in 2 rows, so I can tell where the middle would be. It's in between a 4 and another 4, so the median is 4. Then I split the first half in half to get a first quartile of 3, and then I split the second half in half to get a third quartile of 7. Therefore, my interquartile range, the IQR, is 7 minus 3, which is 4. The LOB is equal to Q1 minus 1.5 times the IQR, so I have 3 minus 1.5 times 4, which equals -3. Therefore, anything less than -3 would be an outlier. But the minimum for this data set was 2, so there are no values small enough to be outliers. The UOB is equal to Q3 plus 1.5 times the IQR. So I have 7 plus 1.5 times 4, which equals 13. Therefore, anything more than 13 would be an outlier, and in this data set, we have 2 values greater than 13. So 15 and 25 are both outliers. Shifting gears a little bit, there is another way to look at the shape of data in addition to histograms and frequency polygons. But we couldn't construct these until we had learned the 5-number summary, and they're also a useful way to graph outliers. So next we're going to talk about box plots. To construct a box plot, we first draw a horizontal axis that includes the minimum and maximum data values. Then I mark Q1, the median, and Q3 with vertical lines above that axis, and I turn that into a box. Then we draw lines out from the box to the largest data value that's not an outlier, and then down to the smallest data value that's not an outlier. And if there are any outliers, we mark those with asterisks. This is a box plot from the example before. I drew the box from 3 to 7. Notice that's our interquartile range, with the median also marked inside the box. 15 and 25 are outliers, and the next smallest point is 12, so I draw a line up to 12 and then mark 15 and 25 with asterisks. The minimum is 2, and there are no outliers on that side of the data set, so I draw a line down to 2. So this is my box plot, and it's sometimes called a box and whisker plot, which makes sense when you see it. In summary, we now have 2 ways to find outliers. Will both ways always agree? No, not necessarily. Let's go back to our second example. If I compute a z-score for 15, would it tell me that it's an outlier? To compute the z-score, I need a mean and a standard deviation. I'll assume this is a population and use my calculator to find both numbers. The mean is 6 and the standard deviation is 5. Notice that the median and the mode are both 4, but the mean has been pulled higher by the large values in the data set. When I compute z-scores for both 15 and 25, the z-score for 15 is 1.8 and the z-score for 25 is 3.8. Because the z-score for 15 is less than 2, this value is not an outlier according to the z-score. So which one do I believe, the upper outlier bound or the z-score? Well, remember that for skewed distributions, we would prefer the median and quartiles, and by extension, we also prefer the outlier bounds. The z-score, like the mean and standard deviation, is not resistant. Also, the -2 and 2 we use to tell between usual and unusual comes from the empirical rule, and this rule only applies to bell-shaped data. Because this data isn't bell-shaped, because it's skewed to the right, we would prefer to use the outlier bounds instead of the z-score, and therefore 15 would be an outlier.